Okay, go ahead, Kirill.
So the paper we are discussing today is called Deep Learning and AdS CFT. It was written by Hashimoto and collaborators. So first of all, let us discuss what an AdS space is. The first three letters of this mysterious acronym. So for now, an entity sitter space is a generic solution to Einstein equations with a negative cosmological constant. So if we write the equations in this form, then they are solved by this metric. It's known generally. It's known as the AdS Schwarzschild black hole. But if we take the black hole radius to 0, in this limit we get just this space. In 3 dimensions.
So maybe you can show the negative cosmological constant, since you mentioned where it is.
This one.
Yeah.
This
so
one.
I mean,
Yes, this one.
not everybody here is a physicist, and so yeah, go ahead.
Yes. So in 3 dimensions we reparameterize.
Maybe one more thing I'll just add so that people know more about it. If you go to the previous slide, this tensor R mu nu is actually a function of G and its derivatives, right? So that's kind of the
exactly.
So all equation one is just for the metric for G mu nu equation.
It's
for
expressed through the Christoffel symbols. Yes.
Yeah.
Yeah.
And then equation 2 is some physicist form of writing components of G mu nu, right?
Exactly.
Where all components are set to 0, only 3 components are not set to 0, which are written here, right?
Yes,
exactly.
So
the first one is G00. Yes, go ahead.
So in 3 dimensions, we can reparameterize it in this fashion. And then we obtain this kind of metric. So we swap the variables for the radial direction from R to eta. And we obtain this kind of metric with these functions. And then these functions at eta going to infinity, both these functions behave at exponents asymptotically, and near the horizon when eta goes to 0, f behaves as eta square and g becomes constant. So now let us discuss the idea of AdS.
Hold on, Kirill, didn't you say that there will be no horizon?
No horizon. No, I didn't say. No, I said near the horizon when eta goes to 0. Yes. So
I thought you were saying that you are not considering Schwarzschild, AdS Schwarzschild.
No, I said that we can get the ordinary AdS space if we take R0 to 0. It's the just yes.
Got it.
So it has these kinds of asymptotics. And now we move on to discuss the AdS CFT. Basically, the basic idea of AdS CFT is that field dynamics in curved space-time can be mapped to in AdS space-time. For other kinds of space-times, such correspondences are not known. Can be mapped to field dynamics in flat space-time with one dimension less. And the extra special dimension, the radial one, is mapped to the renormalization group scale of the CFT. I do not know how to explain this. So basically, this is the energy scale at which we are describing. So the radius at the AdS side corresponds to the energy scale at which we are describing the CFT side.
Well, you can say it's a coarse graining scale, right? So
exactly.
I mean, we really want it to be so that non-physicists can understand something from it,
Yes,
right? You're saying that you have a D minus one dimensional flat space, no curvature, and then you just look at it at different, coarse graining scale, a different level of precision. And then that hierarchy of those theories produces this extra, of course, graining scale, but this extra dimension, right?
Exactly. And this flat metric is usually understood as living on the boundary of the curved space-time.
Right.
Yes, that's the usual interpretation. The motivation is that both are seen as different limits of the same solution, the same supergravity solution in string theory. So basically, again, I'm not sure about going into details there, but when we have, so basically different kinds of particles correspond to different types of strings, very crudely speaking. And then when we have the strings, so there are two types of strings, open and closed. Open strings, so closed strings correspond to gravity, to gravitons, the quanta of the gravitational field. And the open strings produce Yang-Mills type gauge fields. Open strings cannot just hang around in space. They have to be attached to objects which are called brains. Brains, not brains, brains. And yes, and then if we consider a stack of these objects, of these brains, then we will have both open strings crawling on them, producing a Yang-Mills type theory. So like if we move the brains a bit apart, we will have this kind of dynamic there inside. But also the brains will emit and absorb the closed strings. And in different limits, these different kinds of these two types of one or other type of dynamic is considered prevalent. And so the idea is that but there is an actual duality between open and closed strings. So we are considering that these kinds of dynamics actually can be mapped to each other. So so we have an open string description and a closed string description of the same system. The best known example, which was shown by John Maldacena semi-rigorously, is AdS 5 process 5 equivalent to n equal 4 super Yang-Mills. The others are more speculative. So basically, when we have a kind of field theory, we're not sure if it has a gravitational dual, but we can, using some general considerations, symmetries, etc., we can try to guess which kind of dual would it have, and we could compute certain observables and see whether they match.
So you're saying that not for all field theories there is a gravitational dual, right?
Exactly.
But this also works the other way around. Not for all gravitational theories we know field theory
exactly.
dual. So really,
exactly.
the statement that there is this duality is still kind of wishful thinking, right? What may happen is that there are equivalent dual description, but for very specific theories rather than a generic property of like all field theories, all gravitation theories.
Exactly. So on the field theory side, you needed to be a conformal field theory, a special kind of transformation. We will not go into that there because
sorry, Kirill, but conformal field theories you need if you want to get AdS.
Exactly.
But for other types of talking about general duality, on one side there is a
yes, but for other types of spacetimes, they are simply not known.
exactly.
For AdS, we have some somewhat flimsy but still arguments for this. On for De Sitter or for Minkowski, we have nothing of this kind. Yes. So now let us consider a scalar field theory on the AdS Schwarzschild background. Now, assuming that the field, that the scalar field depends only on the radial direction and not on the others, we can write the equations of motion. We also introduce the canonically conjugate variable. So basically, just for those who are not physicists, this is just we take the derivative of the time derivative of the derivative. Oh, it has new. It should be eta there. It should be eta. I have a mistype here. Yes. So we take the eta derivative of the phi and introduce it as an extra variable. And then we can write the equations of motion like this, where the function h is that. For exact AdS Schwarzschild, it's known because we can.
Sorry, Kirill. I thought you said that eta was the radial direction, no?
Yes, exactly.
So it's not the temporal direction.
No, it's not the same kind of conjugate momentum as in ordinary.
Okay, all right.
Yes,
gotcha.
so we are going.
Yeah.
Yes. So we are just going by analogy.
Mhm.
And then now let us discretize them. So phi of eta plus delta eta can be expressed as phi plus delta eta multiplied by pi. And pi can be expressed in this form. We take this expression, we put these terms on the right hand side, so we get the expression for the derivative, and we substitute it here. And then if we want, and then instead of infinity, we take, once we've taken this small step delta eta, then we take some very large number n, and we consider that, and we identify the asymptotics at infinity with n multiplied by delta eta. And therefore, if we know the field values at the boundary, at the very large radii, then using this procedure, we can go auto eta equals 0 step by step, and compute their values at all the points in the bulk. Now the most interesting part, we can write this expression. So basically, we can we can take it to be a 2-vector phi and pi, and we can write it in this form as it's multiplied by a matrix, and then as we have also the potential, we add this kind of term. So we write it as an active, as a functional transformation of this sort.
Kirill, I think there is a question.
Yeah.
Yes. Yes.
So to see if I can summarize the previous slides for, I have a bachelor's in physics, but not an advanced degree in physics. And so just trying to, based on my understanding, it's that there's a complex situation and you can approximate this complex space-time situation as another less complex space-time situation given the boundary conditions. Is that the gist of what we just talked about?
Well, let me try to explain this, Kirill. So basically, the complex situation that you mean talk about is the situation when there is gravity, and that space-time itself really kind of squeezes and stretches, and we don't know how to solve it. We don't know how to quantize it. This is the problem of quantum gravity. In the less complex situation that you're talking about is the one that has no gravity in it. So it's like Euclidean, flat space. And the idea of this duality is that you can map one to another, and it turns out that the simple one actually has fewer dimensions. And so you can think about it as living on the boundary, although you don't have to think about it as living on the boundary.
Right,
But
so
it's
So go ahead,
so,
George.
so instead of having to go through the calculations for gravity, which we don't know how to do quantum gravity yet,
Yeah,
we can approximate it as one without gravity. And
right.
when we approximate it as one without gravity, it turns out we can just focus on the boundaries, and that tells us everything that we need to know.
That's right. Yeah. So it's just reformulating the theory without gravity in one less dimension. Whether you put it on the boundary, that theory with one less dimension, or you just put it, on a separate page in your notebook, it doesn't really matter. It is just a way for you to do complex calculations with gravity as other calculations without gravity. And this only works for very
well,
simple.
but mostly actually people do it the other way, because
Right.
with gravity, yeah.
Yeah. Well, anyways, but this is the gist of it. Yeah.
Yes.
Okay, and then you're going to be connecting that to deep neural networks somehow.
That's where we're
Yes,
hopefully.
but a bit later. For now, we have just the AdS. We're not speaking about the boundary theory. We just have the AdS curved space. That's all.
That's
So,
a difficult one. Yeah.
Yes.
Cool. Figured that if I was confused with a bachelor's in physics, people without any physics might have an even harder time. So
Everybody is
go ahead and ask
confused.
questions.
I can assure you that people with a PhD in physics is confused about that as well. So don't worry about it.
Sounds good. Thanks.
So yes, we can write it as in this form. First of all, linear transformation of this form, and then to account for this potential term, which depends also on phi, so on the first component of the vector, we also take a functional transformation. And now the most interesting thing is that this is exactly what we do in neural networks. So basically this so this is the weight matrix, and this is the activation function. And so basically,
And there is no learning, so it's not really exactly what we do. It is one part.
I will get to that.
Okay,
I will get to that
good,
on next
good.
on next slide. Yes. So basically, the space-time can be represented as a neural network within layers, and in this way, we can get a new perspective on AdS CFT, because basically the whole idea of AdS CFT is that we define some boundary data, some data on the boundary, and we have all the physics defined in the bulk. And in this way, we can see that exactly as we enter the input data on the neural network, we get it propagates inside, and the neural network reaches a particular state. So we can get look at the CFT correspondence in this way. Now our input is these two fields, while the output is pi, the derivative of phi at the horizon. Because we are considering the boundary condition here, also motivated by string theory, these CFT considerations, that the field radial derivative should be 0 at the horizon. And now, if we want it to be binary, if we want it to be just ones and zeros, we take a hyperbolic tangent of pi. And now if we want this, if we take, say, for example, if we take an actual neural network and we want to program it in such a way that it imitates this kind of space-time, then we have to, then we can choose this kind of loss function. So
hold on, so I'm missing it a bit. So when you're discussing the propagation of phi and pi into
yes.
the bulk, That's
Yes.
not learning. That's not learning the boundary. That's taking the information from the
That's not
boundary.
learning. Yes, that's activation dynamics. So
Yeah, but
that's just.
right. So it's just taking
I
the
mean,
information and go. Mhm.
yes. No, I didn't say that it was learning. I said now that that we can make a neural network learn to behave like this. So that's another thing.
You can
This is
learn a neural network behave as it is
as an
ADS.
idea space. Yes.
Yeah,
Yes.
but then you just kind of the answer and you represent the activation dynamics through the neural network that learns that answer. So so
Yes.
then here the learning dynamics is not something additional. Learning dynamics you just use to rewrite your AdS CFT map into language of neural network.
Yes, for now, even no CFT. For now, just the AdS equations of motion.
Well, you
We
start out with some
really-
CFT state,
Yeah.
right? So it is AdS CFT, right?
Yeah.
So I'm just complaining about this learns in the quotation mark because it's not learns the boundary, takes information from the boundary into the box.
Takes, yes,
So it's
yes,
more like activation dynamics.
yes. Mm, mm, mm. So now we have some. So now we have data. So the data corresponding to a real physical system should produce, as I said, pi equal to 0, while other types of data which do not correspond to this, which are not physical in this kind of system, would produce one. So would produce a different type of boundary condition. And therefore, we can choose our loss function to have this form for learning. Now, what they do, they take 1,000 pieces of data corresponding to AdS Schwarzschild. So again, no CFT for now, just the AdS. They make a particular choice for the potential, and another bunch of just randomly generated fake data. This is the map. So this is the real, the phi, and these are the real points which the AdS Schwarzschild would give us. And this is fake data. And then they run the learning algorithm. The first try, the first approximation of the metric is this. It's pretty rough, you see. This is the real determinant, the real function of the determinant, how it goes. And this is the one which comes from the first try. So that here we have the matches in green and the mismatches in orange. But if you run for 100 epochs, the situation gets much better. You have it like this now. So basically around the horizon, it matches perfectly. You only have some deviation at large distances.
So basically the system correctly learned the curvature of the AdS. Is that the
yes,
kind of thing
yes.
that there's only like one parameter to learn, right?
Yes.
And you said near the boundary, as in, so like near the, was that the boundary of the black hole?
No, the black hole is the horizon. At eta going to 0. The boundary is eta going to infinity.
And where is
So
the loss function? And where the loss function is defined at the horizon, right? No.
Exactly. It's pi defined at the horizon. Yes.
Okay. And the input layer is at the boundary at the infinity, right?
Exactly.
Okay, so it goes from the boundary input data to the horizon, and the horizon is where the loss function is defined, and then it back propagates back to the network. Yes.
Yes.
That's the setup.
Yes.
Yes. And where was it that was good, and where was it that was bad? You said it was close to something. It started getting worse.
No, I said that when it takes some random first try at the metric, then of course it doesn't guess perfectly. It produces something like this. But then when we run the learning algorithm and minimize the loss function, so it change the metric determinant in such a way that as to minimize this, then it approaches the reality space.
And how many trainable parameters were there?
How many?
Because there is only one number they had to learn, is the curvature of space. And so if you have many trainable parameters, I would assume that the system may easily overfit. Have they said anything about that?
They did a particular type of regularization for this. So
Okay.
they introduced the regularization terms
Okay.
to avoid
avoid
overfitting.
Okay. Mhm.
Yes.
Yeah. Kirill, what is this initial conditions, phi and pi? What are you feeding physically? What does it mean? Phi and pi.
Phi and pi are some values of the scalar field at eta going to infinity.
Yeah,
So
but what's
some
the training data
solutions of
set? I think Sijo is asking, what's the training data set? What is exactly, do you choose a random phi and pi?
I think they didn't.
So what is this picture of? Is it the phi and pi at the boundary or at the horizon?
At the boundary.
Boundary values, but yeah.
So these are at the boundary values.
Yes.
And the loss function is defined at the horizon.
Yes.
So then that's what, then what is the blue and what is green? Then I don't understand.
Okay, so, well, basically, so,
Maybe we can discuss later.
Yeah, we can talk about that later. Sure.
Okay,
Yeah.
okay. So, so yes, they do this, and then after they average over like 50 metrics, they get something like that on average. And now their next step is to fit experimental data. So they take the magnetization curve of a particular material, and then take it the magnetization as a function of the external magnetic field, and map it to this phi and pi in AdS. So this was the question. Honestly, I had some questions about this part because, in fact, from the AdS CFT, phi and pi are expressed through CFT quantities in this way. So they said something like, so inspired by that, we do this.
Yeah, so they have they have some operators on the boundary theory of that material, and they take those operators and feed into the AdS, and then
exactly,
and then they get something out. But you know what you're going to get out if you are following the RG law. So basically,
exactly, but I had some question that they identified these operators with M and H. Maybe this is correct, but I was not sure somehow.
But it's arbitrary
this
choice.
Is the same as
yeah, it's arbitrary choice. You just pick two operators. You do and then you see how they flow, right? And then you define the flow through the activation dynamics. And so then that also answers your question, my question about this green and blue. You know, you start with whatever initial conditions you want, and then you see where it gets. And before you were choosing random initial conditions for phi and pi, and then follow the dynamics. But here you have a particular, and then you follow the dynamics of the AdS, right? But here you're saying that I don't want to do that. I want to have a particular initial boundary conditions for phi and pi, and that is given by the Hamiltonian of that material probably, right? Or
Yeah,
partition function of the material.
Yeah, so these are the conformal dimensions of the field. So this is the form of the asymptotic solutions. So they behave like the exponent. So when we differentiate, we get these two coefficients in front. So this there should be a minus there. Yes, should be. So then we get, and then they having taken this find pi, they have again ran the learning algorithm. It did find one kind of emergent metric, which did actually fit the data with high precision. So this is the green which fits, and the misfits are blue and orange. So one can see that there exists, that it's an interesting statement from the point of view of AdS CFT, that there exists a particular emergent metric for this kind of system, which does reproduce this with high precision. So our conclusions are that, first of all, we see that this system is able to both learn an AdS metric and to find a suitable metric for the CFT dual and for the boundary dual, and what they and it could also be interesting what they discuss in their conclusion to apply this duality to things like the bulk reconstruction from the boundary. So this research program, which is known as It from Qubit, in which the geometry of the bulk has to do with the entangled qubits at the boundary, and they're considering applying this newly found correspondence to this. And then one of the keys for this may be the black hole horizons. They're also mentioning the another kind of coarse graining in regards to the neural network. So when we are discretizing the network, and it does still does reproduce the dynamics. So the question is, how sparse should our neural network be to be best for finding these kinds of bulk duals. So thanks for your attention.
From that
Yes.
last slide, what is so slide 18? The it from qubit. What is the it from qubit and Mera?
It from qubit is the program to derive gravity and geometry of space-time from entanglement based taking the starting from the CFT correspondence. So
Just a fancy name. It came from Wheeler. He said it from bit, meaning
John
that
Wheeler, yes, John Wheeler, exactly. Yes.
It from bit idea was that everything in the universe should be described as information, and then bit is information, it is physics, right? So it from bit, and then it from qubit is the more recent ideas that maybe it or all physics can be described through not maybe classical bits, but through quantum bits. And Mera is just a particular
ansatz.
It's a particular ansatz for the describing quantum system that uses tensor networks and stuff. And so that network also looks like a discretization of space. Yeah. And so that's why they're connecting. Of course, the rigorously connect all those concepts needs a lot more work than just analogy of things looking like graphs, right?
And ansatz, if I remember correctly, what is like we just assume it's a given, like, okay, assuming this thing is true.
Yeah, if we forget about ansatz, it's just, ansatz is like you're assuming some form of the answer, right? So ansatz as a solution for some equation, you assume it has some form. and then using this form, you see whether
yes.
you can find that's German. I mean, if we had a German person here, they would translate it. I certainly.
All right, so the it from qubit is that, well, so the it from bit was that you can derive the physics or understand the physics from the information.
Right.
And qubit is the modern interpretation where the information is all quantized.
Yeah, but it's all slogans. Those are it's don't take it literally. Just
So
for people who are
basically, basically there exists one particular toy model. So like we have it's called ER, EPR. So we have when we have to entangle the black holes somehow, then they are assumed to be, they are dual to a wormhole geometry. So their idea is that entangled particles in general could be connected by a wormhole, but that's again speculation at this point.
That's way orthogonal to what we described. But let me now add two more comments to this. One thing, I still don't see learning as being dynamical here. Basically, this is more like, here is a system, it's AdS system, and then I want, first you said, and I said, I want a network to learn to behave as if signals propagate on the AdS space. Well, duh, of course you can do that for any system, for any activation dynamics. You just made your system learn it. But learning is not something that you describe dynamically. You didn't attribute to learning any new degrees of freedom, and it was not part of the.
Basically, their idea is that this alpha, beta, and the lambda and the mass of the field all can be, these parameters all can learn.
Yeah,
so
but you learned the parameters that were in your training data set. Okay, so you had a CFT or whatever, theory of this material partition function in there. It was there in the data set. You learned it. Well, of course you will learn it. And in the beginning you said, well, I don't have any theory, but I have a background, which is AdS, and you learned it. Of course you will learn it. What I'm saying that in here, you kind of come to this, learning equilibrium, to the state where a system behaves as you wanted it to behave and you are happy. But nowhere were you treating the actual learning dynamics as a dynamical degree of freedom. There were no, fields associated with the actual learning, right? And that was kind of it was a way for you to obtain an answer that you will obtain. So that's kind of one of my complaints. So I don't think learning dynamics is a part of the dynamics to describe. And the second complaint, there is nowhere here you see any signs of Lorentz invariance, right? So you know about it. And then Lorentz invariance is the crucial and most important symmetry that is between us and quantizing gravity, right?
Exactly. We discussed this before. Yeah. Exactly. Yeah.
So if we are to use this neural networks idea to tackle, gravity in any space-time, then the one first immediate question is, where does the Lorentz symmetry comes from? And there isn't. It's not here as of yet, at least.
Makes me wonder if it could be combined with last week's, where didn't that learn some of the symmetries in the system? So maybe.
Well, that's the point, right? Exactly. That's the whole point. I mean, you do not want to. If it's emergent, then it has to emerge. If it's fundamental, then it has to be in the system. Like in this system that Kirill described, there is no Lorentz invariance. It's not there. Not even approximate one. Now, so I don't even see how it would emerge if it would, because this is just not the part of the discussion. He froze time and discussed how correlators propagate from the boundary where he thinks the input is to the bulk, right? So there is no discussion of the temporal dynamics here. Yeah, but yeah, it's exactly all this is connected, but we just don't have here the description of how that can be done. Other questions?
Yeah, so my doubt is that it is learning the metric, am I right? It is fixing
in the first part, yes.
Yeah, it is fixing the initial condition, and you know what will be the output, because you are putting like out in the output. So then it is like you give the random data, then it learns the metric. So then I don't understand your point that it is not learning that.
My
that
point
is,
was that it doesn't have the learning dynamics. So you're not considering dynamics as a part of the system. Learning, you just said, learn to behave as AdS CFT. So it as AdS. So it learned and behaved as AdS. Okay. Now, now you're saying like, but the learning itself is not the degree of freedom here.
Basically, the problem is that you don't have learning here or here.
That's right. That's right.
Point.
Exactly.
Yes.
So this is just activation.
Okay.
Yeah, that's. Stanislav, you wanted to say something? I thought.
Yes. So basically, as I understand, like correctly, it was a little bit like too much for me. So
it was too much for all of us, and that's why we still don't know how to quantize gravity.
Yeah.
Yeah. So this is one of the like variants of this physics informed. And like we're trying to use at least fragments of analytical solutions embedded into activation functions and loss functions. Is it something?
Actually, only the first, only activation.
Okay.
And that's what my complaint. So
yeah. So if we like put the whole like analytic solution in the like activation, like what the point? Like can we somehow
can we get something new from it, right? So yeah.
Okay.
That was my question.
Looks like
yeah.
Yeah.
Go ahead, continue. Sorry.
Yes. So like that's it. Like, can we try to? And looks like this is one layer, or we started discussing it, like how many layers there, and like are we trying to break analytical solution in some elementary like fragments and
so there are many layers. Kirill, you can show the architecture. There are a lot of layers. The whole radial direction, each step in the radial direction, a new layer. So there are many layerness. There's a lot of layers there, but
and they have same activations or different.
The weights, no, they're different at each layer. So we have they depend. The weights change depending on how the metric varies with the reduce. So we have this dependence here, and for
but how many actual trainable variables there are? That's a good question. That's the question I had, because if like each layer has independent weights, then you will definitely should see overfitting. But maybe they are some kind of connected to each other weights. So the number of trainable parameters is actually smaller than the number of steps in the radial direction. That was a question, Kirill.
If I understood correctly, they are doing a kind of regularization to avoid overfitting.
But that's what I was saying. Like you can imagine, right? So let's say you have this network that you showed, and each connection has an independent weight. No, the network that you have, right? Then there is a bunch of trainable variables. That's a huge dimensional space of trainable variables, and yet you are only training for one parameter, which is curvature of the AdS space. Now, if that's the case, then I would expect to see overfitting, a lot of overfitting. But you said that they're doing some kind of regularization, which, once we understand what that means, maybe we'll understand what really happens.
So about the point that you discussed, so is this a trivial thing? So what we set up, we observe, or another thing is there? So I didn't understand the discussion. So is this a trivial thing? So what we set up?
No, well, I don't know. I don't think it's trivial, but it's expected. That's kind of was my conclusion. I don't know. Basically, the one thing I didn't understand whether there will be overfitting or not. If they do not get overfitting without putting constraints on the weights, then that would be unexpected result for me. And then I would say that there is something there. But if they just train, then it's like physics-inspired neural network. So basically, as was correctly mentioned, if you train the system to produce certain type of activation map from input to output, it will do it. Now, it will do it very well, but it can overfit or underfit. And so if there is no overfitting or underfitting, then it's an interesting result on itself. So why isn't it overfitting? But I think the second idea that Kirill presented is saying that, well, maybe it's a map, right? So it's another language of describing AdS CFT and using neural networks. And if it is, then it's like we have yet another duality. A duality between AdS, between CFT, and then neural networks. And then maybe one of those three languages is more useful for describing one type of observables and not for the others, or something like that. But Kirill can correct me if I'm wrong.
Yes, exactly. They're postulating that it's yet another duality to complement the AdS CFT.
Right. Or another language of writing down the same kind of activation dynamics. So what's missing is that there's still no learning. Learning is there on the trivial, at the trivial level, meaning like you just learn your system to behave. But again, I don't understand overfitting here in this setup. So other questions, comments?
There was a slide 19 and 20 that we didn't go over. Was there anything that we should go over on there?
Yes, this one.
Yeah. Mostly I was just checking to see if there was anything that you need to talk about.
Oh, this one.
Yeah, mostly I was making sure that you had a chance to finish your presentation if there was anything on those.
Oh.
I added it as a technical reference because I wanted to, because I had, as I said, I had questions about this part. So I added it as a technical reference here just to make clear what I was speaking about.
Sure.
Okay, just want to make sure since I interrupted you before you got to slide 19.
And because I kept interrupting you. Yes, it's a good point. Okay, well, are there any other questions? Comments? All right. Thank you, Kirill. I'll see everyone next week. Thank you. Bye-bye.
You're welcome.